Hello, everybody. My name is Gregg, and I'm excited to welcome Bobby Gregg at today's RI seminar. Bobby did his PhD with Mark Spong, working on geometric control and motion planning for three-dimensional bipedal locomotion at the University of Illinois at Urbana-Champaign. He then joined the Center for Bionic Medicine at the Rehabilitation Institute of Chicago as a postdoc in 2010. And in 2013, he started his own group as a faculty at the University of Texas at Dallas. And as recently as last fall, he moved to the University of Michigan, where he's currently an associate professor in the Department of Electrical Engineering and Computer Science, and at Michigan's very own Robotics Institute. Bobby's research interests include control mechanism of biped locomotion with applications to wearable and autonomous robots. These are interests that he and I share, and actually I had the pleasure to work with Bobby within a recent NSF project on low-cost leg prosthesis. And I'm looking forward to learn what is new in his group and environment. He will give a presentation on from kinematic to energetic design and control of wearable robots. So please help me to welcome Bobby again, and you can take it from here.
Thank you, Hartmut,
and doing this.
Sure. Thank you, Hartmut, and thank you everyone for joining me today. So I want to first plug our Robotics Institute. We are a fairly new Robotics Institute, only about 6-7 years old, but we're growing rapidly. Our incoming graduate class is 100 strong, and we're looking for more new students. So if you're graduating with your undergraduate degree or your master's degree, we love CMU students. Also, we do have a faculty search, so we also would love CMU graduates for that as well. So, and we are moving into a brand new, that was not part of it, moving to a brand new building, and we'll be there starting next semester. So with that being said, I want to quickly motivate the topic of my presentation, which is in challenges of human mobility. So in particular, there's more than 1 million Americans who've lost their leg, and a very good number of them have lost their leg above the knee. And additionally, about 1 in 8 adults in the United States have some sort of mobility limitation. This can include stroke, osteoarthritis, age-related immobility, spinal cord injury, and so on. And so there's really a huge need for assistive technologies to address the challenges in locomotion that these populations face. So these populations tend to fall more frequently. They tend to use more metabolic energy while walking than able-bodied individuals, and they tend to walk more slowly and have less range in their locomotion. And so our approach is to use legged robots to bring new assistive technologies to address these problems. And I really do believe that it is kind of a complete cycle where if you can get an autonomous robot to walk on its own, then you can use similar control and design principles to get a wearable robot, such as a prosthetic leg, to walk. And then if you can get that to walk very naturally for a human, in either a prosthetic leg or an exoskeleton, well, then you can make an autonomous robot walk more like a human too. And so then this loop continues informing these different use cases for improving their performance. And so the organization of the talk is as follows. We're going to first go over user-synchronized kinematic control for Agile powered prostheses. So how do we control the joint angles of powered legs? Then we'll talk about quasi-direct drives in powered prostheses. So this is a specific type of actuator that has many beneficial qualities for this application. And then we'll conclude by discussing energetic design and control methods for partial assist exoskeletons. So these are meant to assist individuals who have some control over their limbs, but have weakness that needs to be augmented. So first, I wanted to discuss the conventional approach to controlling a prosthetic leg using sensors and actuators. So the idea is that if you look at the human gait cycle, you can categorize it in terms of several events, starting from heel contact and ending with knee extension, and then it repeats. And so the traditional way of controlling a prosthetic leg is that you develop a unique controller for every one of these phases, and you then have to switch between these controllers as you move along in that gait cycle. Now, that has several challenges associated with it. So every controller you see in this diagram has a set of user-specific parameters, which need to be tuned for every person that uses the leg. Additionally, it's not just parameters within every control mode, it's also the parameters for switching between control modes. So when are you switching from heel contact to flat foot and so on. And so you end up getting this explosion in the parameter space when dealing with this control approach, which can take a very long time to tune for every user. And in fact, it gets even worse when you think about multiple activities. So let's assume that you want to have a leg that can do stair ascent, descent, walk on ramps, etc. Well, then every one of these activities would have its own finite state machine, like we see here, and with its own set of parameters. And so we're talking about dozens, usually more than 100 parameters that could potentially be tuned for every user. It's not that all parameters will change between users, but a lot of them will. And so this is a major challenge to the clinical viability of this technology. And so our approach takes inspiration again from robot walking, where instead of controlling the gait cycle through a sequence of different controllers, the robot is controlled by pretty much a single controller. And the idea here is that as the robot is being pushed forward or backwards by the researcher, the robot is measuring its hip position, it's the displacement of its center of mass, and then controlling the knee and the hip joints to progress forward or backwards based on whether the hip center of mass is moving forward or backwards. And so you get this nice synchronization that the legs are essentially following their walking pattern in synchrony with the center of mass of the robot. So this work was done by Jim Schmiedler at Notre Dame, but the idea actually originates from Jesse Grizzle, and the idea is essentially the concept of a phase variable. And so the idea is that in that video that I just showed you, the phase variable would be the hip's position. And so then as the hip moves forward, maybe this value corresponds to 0% of the gait cycle, and then this value corresponds to 100% of the gait cycle. Well, then you would essentially encode your joint trajectories, which originally maybe you designed them as a function of time, but then you reparameterize that trajectory to be a function of the phase variable. And you notice here that this trajectory is monotonic, meaning that there's a unique relationship between time and phase during steady walking, which is why you're able to do this reparameterization. Now, this is super useful because if you're walking and suddenly you grab the robot and you hold the robot so it can't continue moving forward, well, then it's like the phase variable stops moving forward. And so then you would result in the joints stopping their progression as well. And then as soon as you release the robot, then the progression will resume as if it had never been stopped. It would be phase shifted based on whatever that time delay was. And then when you look at it over phase, if it's a purely phase shifting perturbation, then you actually don't see any transient response whatsoever, because you never actually left the desired pattern with respect to this time invariant quantity that we call the phase variable. It just is able to recognize that the robot has stopped, and then it just continues whenever the robot starts moving again. And so this has been very successful in many robots that Jesse has had in his lab, and most recently the Cassie series. So then this begs the question of, okay, so we can get a robot to walk this way. How do we get a prosthetic leg to walk like a human, and especially to stay synchronized with a human user that is wearing that prosthetic leg? And so we did a biomechanics study led by Dr. Villarreal, who's now at Toyota. And essentially we studied the joint trajectories and the limb trajectories of human subjects under perturbations. And we found that a really good quantity to measure is the thigh angle. And it has, the first reason it's really useful is that it had, the thigh angle is the, first of all, it's the angle of the thigh segment here defined with respect to gravity. And what's nice about it is, first of all, it's a sinusoidal trajectory. And that means that you can build what we call a phase oscillator from it. So if you were to plot the thigh angle versus its velocity or versus its integral, then it would give you this circular orbit from which you can extract a signal that repeats every time the orbit is completed. And so, so it kind of looks like this, where so when you're walking, the sinusoid is moving following its sinusoidal pattern, and this clock is moving with it. And so this clock tells you where you are in the gait cycle. And it turns out that under perturbations, this signal is predictive of the distal joint pattern. So, you know, we're measuring thigh motion, but if you perturb the gait and you're able to measure that thigh motion, well, then it actually is predictive of how the knee and the ankle are going to respond to the perturbation. And so that was very valuable for, information for us to know that we can then use this to essentially predict the motion of the distal segments under perturbations, which is exactly what we want when controlling a prosthetic leg. And so once we have a phase variable, we of course need patterns to follow. And so we start with able-bodied joint kinematics for the knee and the ankle. We start with just, you know, averaged trajectories across subjects, which are good enough to get started. Pretty much, you know, everyone can walk with these trajectories, but they may not be optimal for every individual, right? And so then that's where we have a clinician interface where we allow the clinician to drag control points of these trajectories, so you can have, you know, more push off at the, so this, sorry, this is knee. You have more push off at the ankle or more flexion at the knee, or change the timing of the events. And that allows the clinician to visually do that rather than having to worry about tuning parameters associated with stiffness, viscosity, and stuff like that, which can be cumbersome. So once we have this trajectory, we encode it again as a function of the phase variable. Essentially, we define an output that tells us the desired joint angle as a function of phase. And then we can define our error vector. So this is the measured joint angle, this is the desired, and this is the error. Then we can use a PD controller to drive the error to 0. So essentially driving the measured signal towards the desired signal. And this is done through torque control. Now there's also more principled ways to derive the control law. So this PD controller certainly does not guarantee tracking, but we've done some more rigorous derivations that that can guarantee convergence and stability and stuff like that through the hybrid zero dynamics framework. And this was work by Ann Martin, who's now a professor at Penn State. So this was our first implementation of the concept on a robotic leg. We designed this in-house. We built this all from scratch with very little experience, and so it looks a little messy. We called it Frankenstein, but you know, it had the core components that we needed, such as an ankle and a knee actuator, and had an inertial measurement unit, which was directly above the knee joint, so it allowed us to measure the thigh segment orientation that way. Now I'm pointing out here that the actuators are highly geared. Not to brag, because that's not usually a good thing. And so we'll talk about the consequences of that and dealing with that later. But essentially, it's going to make the system very loud and very stiff. And we'll deal with that during the second part of the talk. This was the first amputee participant to use the leg. And the important point about this video is that this is just the person becoming acclimated to the device. And you'll notice as he's just chatting with us, we're just having a conversation in between trials. And thankfully we had the camera running because we caught this really interesting motion. He was just kind of playing with the leg, just changing his balance and, pushing the leg forward and backwards. And you can see that he has learned how to control the position of the foot through his hips. So essentially, he's learned the mapping from thigh angle to the foot position, according to the way we've defined the joint patterns as a function of that phase variable. And so it kind of gives you like an indirect form of volitional control, which is really neat. And this then allows us to, of course, do walking. And so this video is going to compare passive walking using a conventional leg to the powered case. So it's a little sticky at push off because it's a very stiff actuator, but other than that, it stayed synchronized with the user. And what's really unique is that you can actually walk backwards with it. You can actually take full steps. So that's a maneuver that the subject could not do with their conventional leg because it would collapse beneath them if they tried. We're also able to cross obstacles. And so the way that they're able to do this is that, again, they've learned how to control the position of the foot with their hips. And so they're able to make sure that the foot is sufficiently elevated, and they're also able to rotate over it. So they're able to circumduct a little bit to get the foot over the device, but at least they're able to hold the foot in a known position while they're doing that, which they were not able to do with the conventional leg, at least not without hitting the block. And we can also do things like kicking soccer balls, and we had a little competition, and the participant beat me in terms of the velocity of the kick. So that's not saying a lot, but it was fun. And naturally, we can do steady walking also. What's neat is that they're able to change walking speed seamlessly because it just stays synchronized to the hip motion. So as your hip moves faster, then so does the joints of the robot. And that allows natural adaptation to walking speed. And so what we saw in the study was that as you change walking speed, with appropriate changes in the joint pattern as well, because we also need to modify the joint pattern as walking speed changes, then we actually see a normative trend in terms of ankle work increasing as you walk faster and knee work decreasing as you walk faster. And so you end up getting a net, close to zero, but slight increase in total work. And this follows normative biological trends, which was promising. And then again, this has to do with the fact that the leg is staying synchronized to the user's motion. We also found in a separate study that after one session with the powered leg, it was enough to actually cause noticeable reductions in the amputee subject's compensations. So essentially, when using a conventional leg, the conventional leg certainly does not produce all the function of the missing muscles, right? Because it's passive. And so then the hips and the sound leg have to compensate for the lack of energy injection and braking and so on. And so that is done through compensation, such as hip circumduction and hiking and ankle vaulting on the sound side. And so we saw that when comparing the passive or conventional leg to the powered leg, that we actually saw a pretty noticeable reduction in the prosthetic side circumduction. And we also saw less hip hiking for the powered case compared to the passive case. And then a slight reduction in vaulting. It's still there. I mean, you can still see that this is not this is an abnormal foot progression for normative biomechanics, but it's still a reduction, so it's in the right direction at least. And this is for after one session. So we were hoping that this motivates future work, where if we were able to do additional training sessions, you might be able to have the subjects learn how to no longer utilize those compensations, which of course have been learned over many years. And so now we're working on trying to extend this paradigm from just thinking about continuous phase to also thinking about continuous task. And so the idea here is that after we've designed a controller that can control the entire gait cycle, well, we still have to worry about what is the activity. It's like what are the joint patterns that we're commanding the prosthetic leg to follow. And so that can be done through a classifier, which is the common approach. And so you have these two different levels of control. You have the low level, which is what we'd already talked about, and then you have a high level where you have classifiers or neural interfaces or whatnot. There's many ways to do this. But what we're trying to do now is try to kind of blend these two levels so that instead of having this hierarchy, you have this kind of blended, unified control methodology where, as long as you're able to measure where you are within some activity space. So let's say that you can measure walking speed as a real number, you can measure the ground slope as a real number, and maybe you can measure whether or not you're walking on stairs, and perhaps that could even be a continuum if you're transitioning from walking to stair climbing or vice versa, because there's actually different trajectories that are used during transitions as well. And so this could actually be a real number that represents the progression through a transition. And so if you're able to measure or detect those things, then we could build a model that would be able to predict the appropriate ankle and knee kinematics in a continuous way to allow you to continuously adapt to any speed, slope, or transitional state during locomotion. So that's the big idea. Of course, we're not there yet, but that's the main topic of our ongoing NIH project, where again, we're going to be thinking about stair climbing as well as walking on rough terrains, non-constant slopes, and perhaps even running, and thinking about the transitions between these things, like sitting to standing and walking to stairs and walking to running as well. So that's ongoing work. But this is as we continue to make these controllers more agile, what we're noticing is that the bottleneck is becoming the hardware. So the design that you saw previously, like I said, was very stiff, very rigid, and is not really capable of doing all these things. And so that motivated us to change the way that we were designing the leg. And so we ended up embracing quasi-direct drives, which essentially a direct drive is just an electric motor that is directly attached to the load. Oftentimes, though, you have to use gears because motors don't put out enough torque for the application. And so you reduce speed to increase torque. So a quasi-direct drive is something that just has small amount of gearing. And so in our case, we chose a 22:1 gear ratio through a compound planetary gear set that we see here. And then we chose a very high torque frameless motor from RoboDrive to produce enough torque so that we can still get the meaningful torque that we need after the transmission. And so essentially we're embracing pancake style motors that are a little bit bigger, especially in terms of the cross section, And also may weigh more. They typically weigh more, but they give you more torque than the smaller high speed motors. And the benefit, well, there's many benefits of this. The most immediate benefit is that you have a very back drivable, transparent actuator. So you can freely back drive it with gravity or by touching it. So it's nicely, it's really appropriate for human interaction. And you've probably seen like the Cheetah robot from MIT that has been using quasi-direct drives for some time, and it allows really high performance as well. But I would be remiss if I didn't point out that the Carnegie Mellon leg, designed by Hartmut-Geyer, uses a very similar motor to ours. So I believe that they were the first ones to use a robo-drive motor in a prosthetic leg. But the CMU leg is a series elastic actuator, has an elastic component in series between the motor and gearing and the load. So it is a different classification of actuator, uses a higher gear ratio and stuff like that. So it is different. I do want to point out though that it does have the similarity of the RoboDrive motor and the high torque frameless design. And so in terms of the highlights of this design approach, I want to make some comparisons with our first generation leg, as well as what's often considered to be the gold standard, at least the first robotic leg used in research was the Vanderbilt leg, at least used broadly in the research field. And so that's the one we're comparing against. And so our design is able to very accurately control torque, impedance, and position control. And position, it's essentially as close to an ideal actuator as we've ever been able to get. Has very low backdrive torque, so less than 3 Newton meters. Like I mentioned, very easily back-driven by gravity, which allows us to have very natural swinging motion during walking. Despite having a low gear ratio, we're able to get very high peak torque, 180 Newton meters, compared to about 110 for some of the prior robotic leg designs. Certainly the CMU leg, I think, beats both of these numbers. so we certainly haven't won the prize for high torque, but we're pretty satisfied with 180 Newton meters. It's more than we would need for all the tasks that we've aimed to achieve. Also, we get very low power consumption while walking at fast speeds because we get energy regeneration during periods of braking in the gait cycle. So when you plant your heel on the ground, well, you're actually doing braking so that your center of mass doesn't collapse into the ground, and we can regenerate that energy to the battery. And also, we get sharing between the joints. We've been able to demonstrate that when the knee is doing negative work and the ankle is doing positive work, the joints are sharing the energy directly without even having to go to the battery. And so we end up cutting the power consumption in half compared to the state of the art for comparable walking speed. And also we have very low acoustic noise because we have very few gears meshing, fewer spinning meshing parts. And so it ends up being much quieter compared to our first generation leg. Not many people actually publish data about acoustic noise for their designs, so we don't really have many comparisons to offer for that. But robotic legs tend to be loud. They tend to have, like I said, a lot of spinning parts, and you can hear them. Whereas this design essentially has the same sound level as a household refrigerator or an electric toothbrush. It's very quiet. But there is a downside that I have to acknowledge, that going towards a very high torque motor, you tend to increase the mass of the actuator. And so we've increased the mass by a kilogram compared to the Vanderbilt leg, so by about 2 pounds, which that matters. I mean, this thing is hanging off of people's skin, off the residual limb. And so it does matter, but our argument is that the power and the push off you get from the high performance actuators will actually help launch you into the swing period, so that your hips don't actually have to haul it into the swing period. You don't have to haul all that mass. The actuators at the ankle will actually help you push it up. And we'll demonstrate that shortly, actually. So first I want to show just some videos of walking over ground. And then you'll notice that the walking is very smooth over the treadmill. And this is the back drivability at play here. So you get kind of this free swinging motion, much like a conventional passive leg. Then you get the energetic push-off during weight stance. I do want to point out that the battery is on board, so everything's on board. We do have a cable for data logging purposes, but it's not serving any functional purpose. All right, so we ran a study with 3 above-knee amputee participants where we tried to analyze some more clinically oriented outcomes, so and also the biomechanics. And so we looked at push-off power, and as you would expect, we noticed increased push-off power compared to the conventional passive leg. We also noticed very consistent increase in stride length across all subjects. The push-off power was not really consistent with one subject because if people don't leave their foot on the ground long enough to get the push-off, then you don't get much power. Like if you raise your foot into swing early, then the ankle doesn't have time to deliver that power. And so we had one subject that didn't really get the full benefit of push-off, but all of them did increase their stride length, and all of them did decrease their hip power. And the consequence of that was that when we look at the work that the hip does every stride, we actually saw a decrease using the powered leg compared to their take-home conventional passive leg. And what this means is that the subjects were not having to use their hips as much to pull the leg into swing, which is a compensation for the lack of ankle push-off from the prosthetic leg. So which means that there's less mechanical work, which is of course related to metabolic work, but we didn't measure that. And we also hope that by reducing the hip work, that would also mean that their hips won't be overused over time, right? Because you can get hip osteoarthritis just by overusing it to compensate to use a prosthetic leg. So this was the outcome of that study. So now I want to talk about how we're trying to use some of these methods in exoskeletons. So moving away from amputees, moving to people who have their legs are still intact, but maybe have some sort of weakness or neurological condition that prevents them from having either great strength or control over their leg. And so we're trying to go towards a partial assistance paradigm. So that's distinct from the existing commercialized paradigm, which is complete assistance. So the 3 or 4 commercialized exoskeletons, actually I think there's more now, I should update my numbers. They're primarily designed for people who have severe injuries like spinal cord injury or severe stroke, that really the exoskeleton is designed to do everything for their lower extremities. And so the actuators don't need to be back drivable. They're just very stiff because there's no remnant motion to worry about inside the exoskeleton. And so they can also be controlled using kinematic trajectories, because you don't have to worry about the person's leg trying to go in a different direction than the exoskeleton because the person doesn't have that control. Whereas in the partial assistance paradigm, we want to embrace the fact that the user has some remnant control of their legs. We don't want to get in the way of that. We need the joints to be able to be back drivable enough that the human can move freely without the exoskeleton stopping them. And so that involves both design and control challenges that would eventually, ideally, let us apply this technology to stroke and osteoarthritis and age-related immobility, as well as overuse injuries. And so, as you might suspect, we have adopted a quasi-direct drive design philosophy for this. Similar gear ratio to the prosthetic leg, different motor, but still a high torque pancake motor, where we can get 60 Newton meters of output torque and only 1.5 Newton meters of backdrive torque, at least statically. And this uses a slightly different transmission. It has a belt drive in here, as well as a planetary gear set inside the driven sprocket. So it's a little bit different of a transmission. We have a distributed actuator here, as opposed to a centralized one. But it has a similar design philosophy in terms of the gear ratio and the high torque motor. And this work recently appeared in the Control Systems magazine as well. In terms of the control philosophy, so it doesn't do us much good to design a backdrivable actuator and then command it to track a position that would interfere with the user's intended motion, right? That would be counterproductive. So we actually have been embracing a trajectory-free control paradigm. So we want to throw away the idea of tracking position or velocity trajectories, and instead think about energetic goals, where the human user would still be free to control their own kinematics. And so the idea here is that if you look at the human body, of course, we have limb segments with centers of mass where gravity is pulling on them, and then also those limb segments have inertia that you have to overcome to accelerate or decelerate the limbs in the body. And the idea is that well, we can model all that through the Euler-Lagrange equations. So essentially, we define a Lagrangian function, which is the kinetic energy minus the potential energy. Throw that into the Euler-Lagrange equations, and that gives us the equations of motion. Now, if we throw in control torques from an exoskeleton, they would essentially be an external input to our equations of motion, and we're kind of lumping in the exoskeleton and the human into these equations of motion for convenience. And the idea is that we want to close the control loop around the exoskeleton torques such that the user feels as though they're walking with less mass or less gravity. So essentially we want to close the loop such that the combined human and exoskeleton are behaving like a different mechanical system. So a mechanical system that would correspond to a different Lagrangian function, so a different kinetic energy and a different potential energy. And so that's why we call it energy shaping. So essentially we're trying to achieve a different energy function in closed loop. And so if we can reduce the perceived gravity, then that would reduce the amount of muscular effort that is dedicated to the function of resisting gravity. We could also potentially reduce the amount of muscular effort associated with overcoming inertia. That's more challenging because inertial compensation requires things like matrix inversions and stuff like that. But we have indirect ways to do that. And I do want to point out that my student who first started working on this project was a postdoc at Carnegie Mellon, and now has moved on to Clemson for a faculty position. And I have a new student, Jingping, who's working on it now. So here's our exoskeleton using this controller. And now this is an able-bodied participant. So he has full control over his legs. And what you can notice though is that he's still able to determine his locomotor patterns, which activity he's doing. He's able to seamlessly transition between walking and stair climbing. And this is all because of the backdrivability of the actuators and the trajectory-free control approach. Additionally, we measured the acoustic noise output, and it was less than 50 decibels, so it's also very, very quiet. And we did a study where we had participants do several different activities. So sitting and standing, to walking and stair climbing. And so here's a couple snapshots. Of course, we have papers that show the details, but here's a couple snapshots for, here's one for sit to stand, where we're looking at the vastus medialis EMG, which is muscular effort. And then the red axis and the red plot is the torque from the exoskeleton. So that just kind of shows you how, as the torque is high, we end up seeing a reduction from the baseline. So black is essentially the baseline case of EMG, where you're not wearing the exoskeleton. And you see the active case is when you're actually getting this red torque. And you see the active EMG is drastically reduced because it's helping quite a bit with the sit to stand motion. Also for level ground walking, we look at the soleus EMG. So this is related to push off, which of course is happening right here in the gait cycle. And so we of course get the most torque during this push off period. And we see again this reduction in soleus muscle activity compared to the baseline. And passive is when you're wearing the exoskeleton, but you don't have any torque assistance. And really the only reason we're showing that is we're showing that the passive case is not substantially different from the bear case, meaning that it is very back drivable. So now we also have a newer generation exoskeleton. It's only a powered knee. And it was designed to be a little bit smaller, less cumbersome. It's not quite as strong as the previous design. And the reason is because we want to think of this as a conservative treatment for osteoarthritis or a primary prevention for lower back strain. So the idea is that this would assist weakness or fatigue in the musculature of the quadriceps. So for osteoarthritis, that's relevant because if you can reduce the muscular loads across the patellofemoral joint of the knee, you might be able to reduce an important source of pain that can't be addressed by conventional knee braces because they don't provide any muscular load assistance. And then for lower back strain, the idea is that if we can delay or prevent fatigue in the quadriceps, that might actually help people maintain proper lifting form in repetitive lifting scenarios in the workplace, like warehouses and assembly lines, where you're lifting heavy objects repeatedly. And as you fatigue, you begin to lift with your back, right? And that's where you end up injuring yourself, is when you lift with your back instead of with your knees. And so that's the goal behind this device. And so again, we adopted this quasi-direct drive paradigm where, in this case, we designed a custom electric motor. I don't recommend you do this unless you're really, really passionate about it. Has a whole sort of complications with it. But we got pretty good results out of it. We were able to design encapsulated windings. So essentially, it's a resin material that surrounds the windings, which of course the windings heat up, and you need to get that heat away from them so they don't melt when you're delivering a lot of torque. And so the encapsulated windings help dissipate that heat into the environment. And then we have a 7-to-1 planetary gear core that goes inside the inner diameter of the motor, because we have this large gap here. We're able to design the gear core inside of it, so you get a very compact design. And again, so we can produce about 25 Newton meters of peak torque with less than 2 Newton meters of backdrive torque. So when you're wearing it, you don't really notice the backdrive torque when it's powered off, for example. So here's one of our engineers just demonstrating how it's very flexible. You're able to pretty much do whatever you want when you're wearing the device. It's not constraining your motion, and it's very quiet. In fact, when you use a decibel meter, there is no noticeable difference from ambient noise inside a quiet room. Now, there's probably higher frequencies that are being emitted that can't be picked up by the decibel meter, but that's another story. So this is another study where we looked at lifting and lowering. And so here, we again are trying to assist the quadriceps. And so in this experiment, we had force plates to make sure that the two legs were being equally loaded, because in this particular experiment, we only had one exoskeleton. We didn't put it on both legs. we now have done that experiment, but I don't have it here. But yeah, we have one exoskeleton, and so we have the force plates to make sure both legs are producing the same amount of ground reaction forces. And you're going to see in this video several conditions where we have a bare mode, which is our baseline, and then passive mode, and then active mode. And there's a metronome for timing as well. So this is the muscle activation of the rectus femoris, quadriceps muscle. So here, exoskeleton is being worn, but it's powered off. Exoskeleton's off. EMG activity is very similar to the baseline. Now we turn on the power, and in red you see the torque from the exo, and in blue you see the resulting muscle activation from the rectus femoris. And you see a pretty noticeable reduction in that muscle activity, which is a lot easier to see in this plot. So this just demonstrates how you can, through this torque assistance, we're able to reduce the activity of this particular muscle and others as well. I mean, I'm not showing all the muscles that we measured, but the paper has all the details. So wrapping up here, I want to also highlight some work from Dr. Kumar, who just graduated from UT Dallas, which is my previous institution, and is now a freshly minted postdoc here at Carnegie Mellon, working with Hartmut Geier. And so he was working on adaptive optimization to reduce muscular effort. And so one of the big challenges with optimization of muscular effort is that the cost function is unknown with respect to the thing that you're tuning. And so we don't have a very good expression of muscular effort as a function of ankle stiffness in this particular study. This was a pseudo or quasi-passive orthosis. So this was not the powered stuff I was just showing you, but it can modify its stiffness in real time. And so in Swarov's study, he was using a method called extremum seeking control, which is a way of doing model-free adaptive optimization through perturbing the input to the cost function and then estimating the gradient along the cost function so that you can follow the gradient towards a local minimum. And so he was able to achieve some results that demonstrated reduction in muscle activity of muscles related to ankle motion, and published that very recently in RAL. So we're all very excited for Swarov to now start his postdoc. And this is my last slide. So in closing, we're in the middle. We're certainly delayed now because of COVID-related restrictions, but we're in the middle of assessing functional outcomes in stroke subjects using these exoskeletons, as well as assessing muscle force and posture during lifting and lowering in able-bodied subjects. And we're just getting started thinking about assessing muscle force and pain in knee osteoarthritis subjects, again, using the knee exoskeleton. And so that work will be ongoing and hopefully get ramped up as the pandemic gets more under control. So finally, I just want to thank my funding agencies and the students and staff who made this work possible. Again, this work was done both at UT Dallas and at Michigan, and I'm very happy now to answer your questions.
Okay, thank you very much, Bobby, for this nice and broad overview of your research trajectory in the assistive robotics domain. Please, we open this for questions. We can just, if you just raise your hand, I can point to. Of course, always no one wants to go first. Maybe I can ask you a question then. When I saw your earlier slide on the backward motion, you mentioned that it's possible to do a backward motion, but what to me, when I looked at this, it looked a bit awkward still, the movement. And I would presume that humans normally, when they move backwards, use a different trajectory or
Yes,
different leg behavior.
that's exactly why.
So how would you say it is possible to embed a multitude of desired trajectories into the phase-based approach? Or what are your ideas of going away? You mentioned a little bit energy-based shaping, perhaps, but I
Yeah,
was
I mean,
curious if you could.
right, yeah. So we've certainly thought about the energy-based approach for controlling prosthetic legs, but then you really got to get it really right to get the right kinematics. That's the big challenge with prosthetic legs. But yeah, you're absolutely right that the backwards walking is not following a normative trajectory because it's literally a forward walking joint pattern in reverse, right? Now, if we were a little bit savvier at the time, we would have just programmed a different set of kinematics when the phase variable is going backwards, right? In theory, it's a pretty easy thing to do. You just, yeah, when the direction's this way, you use a backwards trajectory set. When the direction's this way, you use a forward trajectory set. So there's nothing theoretically stopping us from doing that other than the fact that we just didn't do it during that study.
Okay, and how would you generalize it to perhaps other behaviors? Could you still do that?
Yeah, with other behaviors, that's when things become more difficult. So that's where so that kind of gets to, let's see if I can find it. Kind of gets to this idea where if you're able to parameterize the behavior somehow in a model of the joint kinematics, then this framework can work. And so essentially it's like extending the dimensions of our model, which previously the model was just as a function of the phase variable, right? But now what I'm proposing is that the model is a function of other dimensions as well, such as speed and ground slope. Maybe whether you're where you are in a transition between stairs and walking. But I think the main limitation of this approach, though, is that it has to be some sort of parameterizable behavior, right? You have to be able to quantify it in terms of some activity space that we're describing here. It has to be cyclic to a degree. I mean, at least when for a constant point in your activity space, it has to be cyclic. So those are kind of where this approach hits its limitations, that it might be difficult or impossible to do arbitrary foot motions.
Okay, thank you. I see a question from Rahul.
Hi, so thanks for speaking today. You touched a little bit on the physical compensations and imbalances that can accompany conventional prostheses. And I'm curious about how the musculature of the amputated limb could play a part, specifically in things like muscle atrophy, where it may not be noticeable day to day, but it could compound over months or years.
Yeah.
What are your thoughts on how changes like this could impact gait consistency over time with powered prosthetics?
Yeah, you're absolutely right that there are anatomical changes, especially around the amputated limb. So, in fact, that's what our reviewers pointed out for that particular unpublished study. That yeah, we're only addressing compensations that are strictly because of the biomechanics of the prosthesis, but there's also compensations associated with anatomical changes, either due to the amputation itself, right? Because they have to tie down the muscles in certain ways, and there's different ways to do that, as well as atrophy that could be attributed to different types of compensations. So I think that the compensations we're aiming for are the ones that are purely a function of the abnormal biomechanics of the prosthetic leg. Maybe over time we could start addressing some of the things like you mentioned, like atrophy. Like maybe if they start using their muscles in a more normative manner over time, then maybe atrophy will reverse. But honestly, though, when you have those anatomical changes, you have biarticular muscles that can't span the knee anymore. There's some things you just can't address with this type of stuff.
Thank you. We have another question from Ashwin.
Hi. So I had one question about the idea of using kinematic trajectories conditioned on this phase variable. So since different types of people have, like, based on their heights and body structure, their walking pattern. So in that, for a prosthetic, you would want that it can work with people of different bodily structures. So is this idea of using kinematic joint trajectories really that sound if you want your device to be adaptable to different subjects?
Right. Yeah. Because you still have to a degree, you still have a tuning problem, right?
Yeah.
So I hear you there. And yes, everyone's gait patterns are unique, right? And so our philosophy here is that, okay, start with averaged gait patterns as a starting point, get people walking, and then we can tune to make it more optimal and personable. And so I talked about the graphical way that we tune things. But what I haven't really talked about, we have a very recent paper. I don't even know if it's been, yeah, it actually hasn't even been presented yet because it's for Biorobe, which is hasn't happened yet, where we show that if you have a multi-dimensional model like this, and if you tune just the level ground walking trajectories for maybe a single speed. So let's say I tune 1 point in this activity space, the kinematics associated with 1 point in this activity space. Well, because the model is a continuous model, you can actually distribute some of those individual features across the entire space. Okay, so the idea is that you can leverage the fact that if you were to build a continuous model of the kinematics as a function of speed, slope, phase, whatever, and then you tune, let's say, 1 point in that model, and you weight that very heavily, and then maybe you re-optimize the model. Well, then you can actually distribute some of those subject-specific features across all of the activities. I'm not saying it's going to be perfect, right? But because it's not entirely clear how much a customized walking gait would affect a customized stair climbing gait, you know. But it gets us closer. So we are looking at ways of efficiently tuning these systems and leveraging the continuity of the kinematic model.
But the tuning would also involve changing the nominal behavior then, according to the subject, or it's what level of tuning would you mean?
Okay, so the tuning that we do is typically like visual. We have the subject walking back and forth, you know, in front of us. We work with a clinician, and clinicians are really good at visually observing, you know, abnormalities in gait, and then the clinicians can then tune the trajectories for that level ground walking gait, and then we can distribute those features across other activities.
Thank you.
Mm-hmm.
Yeah, so a question by Russell.
Hi there. I have a question. Have you ever tried other phase variables besides the side angle? Like I read a paper from your lab, like the integral of the side angle, probably another choice for the phase variable. So
right.
Which determine this is the best choice for the phase variable?
Yeah, I kind of glossed over that. But this is a backup slide. So we don't use the thigh integral by itself. We use it as one of the axes for this clock that we see here. So you have like thigh angle versus thigh integral, and that gives us through atan2, it gives us this phase angle. Okay, so we do use thigh integral with the thigh angle. Alternatively, though, we have what we call a holonomic version, where it only uses the thigh angle and that's it. But then you have to know when to switch from stance to swing because the direction is not purely monotonic across the whole gait cycle, right? So this one, the phase angle is always increasing during forward walking, but this one is not, right? So you have to know which part of the gait cycle you're in. So they each have their advantages. So this one's really only useful during rhythmic walking because you need to have a well-defined orbit here. And as soon as you stop walking or you walk kind of arrhythmically, then this well-defined orbit will collapse on itself, or it'll just become misshaped, and then bad things happen. And so that's when we rely on this type of phase variable, where it's purely based on thigh angle, a position measurement, and then some switching logic to switch between the different periods. There's other phase variable options, like shank angle can be used as well. Tom Sugar at Arizona State University has used shank angle and had a lot of luck with that, but I don't think he's ever used it to control a knee though. He's used it to control an ankle.
Okay, thank you.
Mm-hmm.
I can ask one more question. You have been in this field now for about 10 years, right? If you reflect back on the trajectory that the field is taking, what do you think like the next generation of young researchers should be focusing on? What are the like 2 or 3 key areas where you think the gain we can make scientifically is really large?
Yeah. Well, you all have asked me some really good questions about the downsides of relying on predefined trajectories. So if you can figure out a way to maybe do model predictive control to do trajectory planning in real time as you're walking in a reliable way, that would be awesome. That would really make a big difference, because then you get to the point where you can do things like arbitrary motions, right? And really something close to volitional control. But I think I'm not the expert to make that happen. But maybe someone in this audience is. So I think that's a really important area of trajectory generation. I also think neural interfaces are going to be a huge area too. People like Doug Weber are working on that at Carnegie Mellon, and there's a lot of potential for trying to integrate neural feedback, neural information with these lower level feedback loops. So I think those are both really exciting areas.
There's one more question from Ashwin.
Hi. So about the first idea that you was talking about, the model predictive control, what would you say are the bottlenecks? Like, we've seen that people have been able to do model predictive control for quadrupeds. So maybe compute is not the problem. Then is it the problem that we can't get good enough models for the system because you have this human in the loop, and that's what screws things up? Or what are the challenges specifically?
I think the model the human is one thing, because that's really difficult to model. But it's not just like the physiological, it's not just the physical parameters of the human that are difficult to model. It's also like, what is the human trying to do, right? And so that's really the hard thing. So if you're trying to do prediction, well, what you're really trying to do in this application is you're trying to predict what the human wants to do, right? And that's a hard thing without having access to their brain or peripheral nerves or whatever. But maybe you can get some information from body mounted sensors. Maybe you can take cues from the human body to help you predict what that motion is going to be. But yeah, I mean, I think that's the main challenge, is that you don't really know what the intent of the user is.
Okay, I believe there are no more questions. Let's thank our speaker, Bobby Gregg, again for a wonderful presentation in the assistive device domain. Thank you very much.
Thank you.
I hope to see you at some point in the future.
Yeah. Thanks, Hartmut. Thank you, everyone. Really appreciate it. Hope to see you at the next in-person conference. Yeah, feel free to follow up and email me if anyone has questions. Happy to talk later. All right, I'm signing off. Bye.
Bye-bye.